Yeah, one more thing, Malthe, before we get started.
Yep.
We usually record these pre-seminars as well as the main seminar and post them on the seminar page and YouTube. Are you okay with that? Or
Yeah, no problem.
okay, perfect. All right. In that case, I think we can get started. So, welcome back, everyone. For today's pre-seminar talk, we have Malthe Mejlsted from the University of Münster, and he will be talking about a background on amenability of actions, cross products, and nuclearity. Take it away.
All right. Thank you very much. So, yeah, thanks for this opportunity. So this talk will be a little bit of background material for Jamie's talk. So I'll try to introduce some of the relevant notions and some of the different relationships between these notions. So the main goal of today will be to try to explain the words in the title of this paper by Jamie and Shirley and David, which is stable rank 1 in non-nuclear cross products. And then added the word simple because that will be an important assumption as well. So I'll try to explain what these words mean, and I will also try to explain where these type of cross products come from and why we should be interested in looking at simple non-nuclear cross products. So the first of these words is this condition of stable rank 1. So what does this mean? So unital C-star algebra A has stable rank 1 if the set of invertible elements in A are dense in A. And this whole idea of a stable rank is one way to try to generalize the way of the concept of a topological dimension for abelian C-star algebras. And indeed, for a C-star algebra, an abelian C-star algebra CFX, this has stable rank 1 precisely when the topological dimension of X is less than or equal to 1. So there are different ways to try to generalize this concept. You also have real rank as another one, but this one is a very suitable notion for certain types of constructions. So um, there's also a more general formula for this stable rank and the relationship between stable rank and the topological dimension of a space. But this stable rank 1 case is very special and has a lot of relations to other areas of C-star algebras. Um, this condition has a lot of nice permanence properties. Among others, it's preserved under direct sums, it's preserved under matrix amplifications, and preserved under inductive limits. So this means that we can already see quite a lot of examples of stable rank 1 C-star algebras. It's very easy to see that the complex numbers have this property because all the invertible elements are everything except 0, so it's clearly dense. And then we can also see that all finite dimensional C-star algebras must then have stable rank 1 because of this preservation under direct sums and matrix amplification. And then from the inductive limits, it follows that all AF algebras have stable rank 1. So really, there are quite a lot of interesting examples of stable rank 1 C-star algebras. It's not too difficult to show that a necessary condition for having stable rank 1 is that the C-star algebra should be stably finite. And already from this stability of the matrix amplification, it follows that to prove this, it just suffices to prove that stable rank 1 implies that A is finite and not stably finite. And this is not too difficult to prove. You can, for example, look at some non-unitary isometry, and then you can look at its distance to the invertibles. And then this a clever argument shows that this works. But again, these two concepts of stable rank 1, which really says something about there has to be a lot of invertible elements, it is sort of in the same tune as finiteness, which just says that you can phrase it as, for example, that all right invertible elements are left invertible. So in some sense, they are both properties dealing with invertible elements. So it's sensible that there should be some connection here. So this is the first of these words in the title, is stable rank 1. So which C-star algebras do we want to try to establish this property for, or maybe just examine this property for? We want to examine them for cross products. So what are those? Cross products are C-star algebras associated to group actions. So which kind of group actions are we looking at here? So we're looking at countable discrete groups. We'll denote the unit by E. and we're looking at compact metrizable spaces X. And we'll always be considering groups actions by homeomorphisms, which is just a group homomorphism from G into the group of homeomorphisms on X. And we'll write this G curve arrow X for the group action. And when we're only dealing with one group action, we'll just write Gx for the action of alpha of G on X. So the examples that one should keep in mind should be actions, for example, of Z to the D or of the free group on D generators on the Cantor space. These are very classical examples of countable discrete groups acting on a compact metrizable set. So how do we relate these group actions to C-star algebras? We do it by constructing the cross product. So very briefly, if we have a group action, we can consider the set of finite formal sums where we have the coefficients to be these Fs, which are just elements of Cx, and the Us are unitaries indexed by G, such that sending S to Us is a group homomorphism from G to the unitary group. And this space of formal sums can be endowed with a pointwise addition, and we can also define an involution in this way by saying that U star S should be U of S inverse, and a multiplication in this way, where when you conjugate F by US, you get the action of S on F, where this just means that you precompose with S inverse and then apply F. So what this really says is that we can somehow encode the action of the group G on the space X into the multiplication structure of this set. So with this addition and involution and multiplication, we get a star algebra. And this star algebra contains in a very canonical way the group G by taking all of the formal sums or by just taking all of the unitaries US. It contains a canonical copy of Cx, which is if you just consider all of these sums where you only have one term of U, which is U of the identity, and then consider varying all the coefficients. And it also contains the data of the group action built into the multiplication in this star algebra by this formula here. So really it captures the data of the group action. Now it's a star algebra, but we would like it to be a C-star algebra, so we should somehow complete it. And there are different ways to do this. We can either choose to complete it in the reduced norm or the universal norm. So the reduced norm is a norm that we can define by considering some regular representation of our group G and get some technical construction. And we can take the closure of this star algebra and get the reduced cross product denoted by this R for the reduced cross product. Or we can take the universal norm, which is more about taking the supremum over a lot of different norms, and then we get the full cross products. And both of these are interesting to look at, but we'll be focused on the reduced cross product for this talk. And these two norms, they might coincide or they might not, depending on the group action. And we'll return to that in a bit. So now we have established that a group action gives rise to a C-star algebra. And the question is, how do we translate different properties of the group action into properties of the C-star algebra of this cross product? So we will restrict ourselves to some certain kinds of actions, which are particularly nice because they will help us say more meaningful things about our C-star algebras. So one point before that. This construction of the cross products has some very nice properties, and as I mentioned, the reduced cross product contains CFX in a particularly nice way, in the sense that it's actually a Catan subalgebra. But for now, the most important part of that is that we have a unique faithful conditional expectation from the reduced cross product down to CFX. And this is just extending this projection of picking out the coefficient in front of U of E, where E is the identity. And this means that we can actually go back and forth between some C-star algebraic properties of CFX and of the whole cross product. So uh, one of the important applications of this is to consider how the traces look on the reduced cross product. So we in fact have a one-to-one correspondence between traces on the cross product and G-invariant probability measures on X. And the way to see this is that if you start with a trace on the cross product, then you can just restrict this down to CFX. And this is now something that gives you a probability measure by Ries's representation theorem. Whereas in the other direction, if you have a measure on X, this gives you a trace on CFX by just integrating with respect to this measure. And you can extend this to the whole cross product through composing with the conditional expectation. So we really have a very nice way of going back and forth between some traces on this C-star algebra and something which is a priori maybe not a C-star algebraic, namely G-invariant probability measures on X. So something that is very much to do with the group action. All right. So yeah, we want to relate some of the properties of this group action with some properties of the C-star algebra. So we will require two important properties of this action, namely that it should be minimal and it should be topologically free. So what does this mean? So we consider a group action and we say that a subset y of x is G invariant if G of y ends up in y for all G in G and y in y. So sends this set y into itself. And we say that the action is minimal if there are no other closed G invariant subset of x than the trivial ones, which are the empty set and x itself. So the reason why these G invariant sets, closed G invariant sets are interesting is because if you have a dynamical system, if you have a group action and you have a closed G invariant set, then you can restrict your action to that set and you get a new system, new dynamical system. And by a Sonn's lemma argument, you can show that each dynamical system actually has a minimal dynamical subsystem. So in some way, these are like the irreducible, in some sense, subsystem, reducible group actions. So it makes sense that we try to work with these building blocks. Another important condition is that of topological freeness. So we say that an action is topologically free if the set here of all the points in X where the stabilizer is trivial forms a dense subset of X. And by the stabilizer here, we mean the stabilizer at X, we mean all the elements in G that fix the point X. So this is a generalization of what it means for an action to be free. So an action is free if all the stabilizers of every point are trivial, but now we require something that is slightly weaker, namely that they don't have to all be trivial, but that the set of points where the stabilizer is trivial should be most of the points in the sense that it should be dense in X. So one example, like a very geometric example of this, could be if you consider the action of set by on the unit circle, the unit sphere in 3 dimensions by an irrational rotation around the z axis. So this is an action that is definitely not free because all of the elements of your group will fix both the north and the south pole. But it is topologically free because these are the only points that are fixed, and every other point has trivial stabilizers. So this means that we still have that this set here consists of all the points that are distinct from the north and south pole, and this is definitely dense in the sphere. So in this way, this concept is a generalization of freeness, and it is the appropriate notion in a lot of these results about crossed products. And one of the reasons for this is that we have this result, this theorem here by Archbold and Spielberg from 93, which says that if we have a group action that is minimal and topologically free, then the reduced cross product is simple. Simple here meaning that it has no non-trivial closed ideals. And this is by no means a trivial result, but it maybe shouldn't be too surprising that there is some correspondence between these notions of minimality and topological freeness to the ideals of the reduced cross product. So the way that this is shown is that you can use topological freeness to show that the ideals in the cross product will be related to some of the ideals inside of Cx. And then this minimality of the action allows you to be able to um, relate or to show that non-trivial ideals inside of the cross product will somehow still give you some non-trivial um, invariant subsets of X, and then they will need to be everything because of the minimality of this action. So it is definitely there is something to prove here, um, but these two properties are somehow not that unnatural when you're considering group actions. So this explains the kind of actions that we're interested in, and this gives us the simplicity of the reduced cross products that we're interested in. Now, so we restricted ourselves to the case where we assume that our groups are countable and discrete, our spaces are compact and metrizable, and we have assumed that the action is minimal and topologically free. And these seems like reasonable assumptions, but they also kind of restrict ourselves quite a bit. So an interesting question could be asked, should we also assume that the groups that we work with are amenable? And you could do that and you would gain a lot of structure on your cross product. But if you don't assume, but you also exclude a lot of interesting examples. So we really want to be able to consider examples like the free group acting on the Cantor set. So let's try to examine what would be gained or lost by assuming or not assuming amenability of the group. So amenability of groups is interesting in a lot of context, but for group actions, the main point here is that we're really interested in amenability of the action itself. So let prop of G denote the set of probability measures on G, viewed here as a subset of L1 of G. And for elements of the group G and for probability measure mu, we'll define G dot mu to be the probability measure on G that's given by precomposing with G inverse on any set. Now we can define what it means for an action to be amenable. So an action G and X is amenable if there exists a sequence of continuous maps, these mu n, from G into the space of probability measures, such that this condition here holds for all G. And this is somehow an approximate invariance condition. And the point here is that this looks a lot like the condition for a group to be amenable. And indeed, if you just assume X to be the one-point space, then you see that a group is amenable if and only if it acts amenably on the one-point space. But the point here is that you now have some more freedom in that you can choose you can that instead of just having a sequence of probability measures, you can now have these functions being something that depend on the points in X. So it gives you some more freedom of how these actions can look. So it's easy to see that if you have a group that is amenable, then any action of that group will also be an amenable action. And this is easy to see because if you just choose this function or these functions here to just be constant functions that map into the sequence of probability measures witnessing amenability of G, then you see that the action is amenable. But in general, the converse doesn't hold. So if we assume amenability, we get these nice actions, but we can also have actions of non-amenable groups that are amenable. So this doesn't hold in reverse. So why are we interested in amenable actions? We're interested in them because they will have a very nice C-star algebraic property of the cross products, namely nuclearity. So there are many different definitions of nuclearity. Here was one. We say that a C-star algebra is nuclear if for each finite set f and a and each epsilon, we can find some natural number and completely positive contractive maps from A into the matrix algebras on n dimensions and back from the matrix algebra into A, such that if you compose these two functions and apply them to A, then they'll be very close to A for all of these finitely many A. There are many different definitions. This is just to highlight that this is something that can actually be checked. And in some cases for matrix algebras, for example, for finite dimensional C-star algebras, this is easy to check. But maybe a more enlightening way to see what nuclearity means is this equivalent definition that A is nuclear if for any other C-star algebra B, the algebraic tensor product A tensor B admits a unique pre-C-star norm. So this is another way of saying that you have these two possibly different norms on the tensor product, the minimal and the maximal tensor product, and being nuclear says that these will always coincide for every C-star algebra B. So this case reminds us a lot of the situation that we're in for group actions, namely that we have this reduced cross product and the full cross product. And indeed, it holds that nuclearity implies that the full and the reduced cross products coincide, which is a very nice property to have. So this is really something that makes our lives easier when studying cross products if we have nuclearity. And this relates to amenability because we have the following theorem by Ananthararaman, Delaroche, and Renaud, which says that if you have an action of a discrete group on a compact Hausdorff space, then the action is amenable if and only if the reduced cross product is nuclear. So putting this together with what we have from the previous slide, we see that if we have an amenable group, then the action will be amenable, and the action is amenable if and only if the reduced cross product is nuclear. So restricting to the amenable case of groups really gives us this very nice property of reduced cross products. Now, the question is, we know that the first implication is not reversible in general. So it might be the case that if we have that all the interesting actions of non-amenable groups that we're interested in, it could be that all the actions are in fact amenable and we would always be in this nuclear case. But it turns out that this is not the case, and we will discuss this now. So what happens if G is not amenable? So let's now focus on this implication here and look at the setup where we have an amenable action. So if we have an amenable action of G on X, then we can actually we can actually establish amenability of G if we can just show that there exists a G invariant probability measure on X. And this is an if and only if, as long as you're in the case where the action is amenable. So for our purposes, the interesting direction is going from right to left. And you can prove this by using this G invariant probability measure on X to average your sequence of functions coming from the definition of the action being amenable. And then you are averaging this out, and this just gives you a sequence of probability measures, and you can check that this witnesses the amenability of G. So we can have like a partial converse to this implication here in the case where we have a G invariant probability measure. So whenever we have a G invariant probability measure on X, we have this conclusion that G is amenable if and only if this reduced cross product is nuclear. So we might ask, the actions that we could be interested in of some non-amenable groups, do they in fact admit some G invariant probability measure on X or not? And this is where we return to what we started off by talking about, which was this stable rank 1 condition. So if you want to look at cross products that have stable rank 1, then they must in particular be stably finite. And a result by Kunz shows that for all unital simple C-star algebras, being stably finite is equivalent to the existence of a normalized quasi-trace on A. So the point here is that this condition of having a unital simple C-star algebra can be fulfilled in our case because we applied this result to the cross product of a minimal topologically free action. This is automatically simple, as we've discussed, and this is also automatically unital. And then we see that if we also assume stable finiteness, then we have the existence of a quasi-trace. And in this case, we can restrict the quasi-trace to CFX, just as we did with the traces, and then we can get a G invariant measure on X. So this means that in the stably finite case, from a minimal topologically free action, we will always have such a G invariant measure. So in conclusion, if you consider these minimal topologically free actions, and we assume that our target cross product C-star algebra has stable rank 1, then we see that G is amenable if and only if this cross product is nuclear. And this means that if you want to consider actions, for example, of FD, some non-amenable group, then we will necessarily end up in the non-nuclear case because of the assumption that we are searching for things with stable rank 1. And this means that we really need to consider this case of non-nuclear cross products. It can really be avoided, which is too bad because having the reduced cross product and the full cross product coinciding gives you some more options. You can work with the reduced cross product, but still get this universal property of the full cross product. But unfortunately, we're just simply not in that case. So we need to somehow develop some tools for working with non-nuclear things. All right, that was all I have to say, and here are some of the references.
Thank you, Malthe, for the great talk. Are there any questions from the audience?
Sure. Do you please show the page 12? Oh, no, before this. Okay, I just...
This is a very brief explanation of something that, and we are only using this in this case where we are talking about cross products of actions on spaces, and we have all these assumptions of a countable discrete group and compact metrizable spaces. So some of these things are might be a little more complex in general, but this is the statement in this reduced case.
Yes. Okay. I want to see that is the chaos trace, not trace. Okay. So so if it is exact, then it means just trace.
Yeah.
Okay, thank you.
Can some of these things be generalized to when you have an action not on C of X, but on some non-abelian C-star algebra?
I think some of these results definitely work, but I am not sure how much of it can actually be generalized. That's I think that's I'm unable to answer that in any meaningful way.
Yeah, okay, thanks. Okay, is there at least a definition of what it means to be an amenable action on a non-commutative C-star algebra?
I think so, but I'm not actually quite sure about that. I will refer that question to if anyone asks Jamie that for his talk. I think he'll know a lot more about this than I do.
Okay, Bishan just said that there is a. Thank you.
Thank you. This is a naive question from a non-analyst. So I hear about in this seminar non-amenable groups a lot. And then you ask a question like, what is an example? And everyone goes, well, of course, the free group. What's another example?
Well, at least to me, like the free groups are the main example, and there are definitely others, but then a lot of the non-amenable groups that I at least know of are somehow characterized by some other properties, so they're not maybe as directly constructed. So if you look at some like growth rates of groups, then you can also see that if you have groups that grow like exponentially fast, then they will also be non-amenable. And there are definitely examples of that category. That's also a way to see that that the free groups are not amenable. But to give you like concrete examples off the top of my head, I'm not really able to do that. But to me, at least, knowing that the free groups are non-amenable is like it is just an example, but it is also maybe one of the more important examples. And for example, for these kind of group actions, this is really often what we're interested in because now I mentioned just like some action, which is rotation on the sphere, and having an action by having like one homomorphism is very nice, but if as soon as you just have two homomorphisms that don't really have any interaction, you get an action of the free group of two elements. And these kind of things are actions that we are actually interested in, having some different homomorphisms with minimal interaction playing together on the same set. I hope that answers at least partly your question.
What does it mean for a group to have exponential growth precisely?
Yeah, so if you have some finite set of generators, then you can like define a word length function, and then you can see like count the number of words in your group with a certain length. And if you see how these like balls of a certain radius, how the number of elements grows compared to the radius of the ball. And if this is exponential, then it grows so fast that it can't be amenable. Whereas if it's polynomial growth, then it will be amenable.
Okay, good. Thank you.
Yeah, no problem.
It's another example. Okay. SL3Z.
Yeah.
Okay, thank you.
So you mentioned that for a group G acting on X, there's this one-to-one correspondence between the traces on the cross product and the invariant measures. But does that not require something else about the action, like it's free or something to?
Yeah, I might have possibly.
Yeah, I think so. I just wanted to.
Yeah. I think I might have gotten some condition there. Yeah, that's the problem with always working with particularly nice objects. You kind of sometimes forget what.
Yeah.
Yeah.
Yeah. Fair enough. Okay. Thanks.
Any questions from the online audience? There is no online audience. Okay. All right. In that case, let us thank Malthe once again. And we will take a 10-minute break before Jamie's seminar.